Okay, problem number 35 is about shadow length, and it talks about a man who is 6 feet tall, and he's walking at a rate of 5 feet per second away from a light that's 15 feet above the ground. So the 15 feet right up here, that represents the height of the lamp post. Now he's walked away to like 10 here, okay? So I know that at this point he's 6 feet tall. So he is at X is 10, Y is 6. So I wrote that point there just to try to help out a little bit. He has walked 10 feet away. It says from the base. When he's 10 feet away from the base, what's the rate? At what rate is the tip of his shadow moving? So his shadow is projecting out. Let me draw his shadow like in green or something. His shadow is here, okay? And so when we're looking at the shadow, we know that let's look at these triangles that we've kind of gotten formed here. We have one that's 15, and then we don't know maybe what y is here. Okay, so I kind of drawn a little picture here. We've got two similar triangles going on here. The larger right triangle we've got going on here, I'll draw the right angles in. We're 15 feet high. He is 6 feet high. Now he is moving. He's out here at an X of 10, and that changes as he's moving. So if you think about it, we could represent the variable, like the whole length here is y, just to go ahead and use that variable. Y could be as big as 15, but again, we don't know how far out he is. And then y minus x, like for instance, he's 10 feet out now, so however long the shadow is, if I call it y, the most it's going to be is 15, because the lamppost is 15 feet tall. The most that's going to be is 15, but if I call this whole distance y, and he's at x equal 10, y minus x would represent, right here, how long the side of this smaller right triangle is. So what we've got is two similar triangles. We could say, you could make different kinds of, however you wanted to build your proportion, but I'm going to say 15 goes to y the way that 6 goes to y minus x. Just comparing those sides of those similar right triangles. Now if I want to get an equation from this, what I can do is cross multiply. 6y is equal to 15y minus 15x. It's 15 times y minus x, but just to save space on the iPad, I'm going to go ahead and multiply that out. Now if I want to get my y's, let's get all my y's on the same side. I could move the 6y's over here. If I subtract them from both sides, that would be 9y here. Let me add the 15x over to this side, and if I solve for y, 15 over 9x is equal to y. I'm just going to go ahead and write it with a y on the left-hand side. That reduces to 5/3 x. So that's an equation that might represent, if he is 12 feet out from the base of the lamp, how, what is the tip of his shadow there, because the tip of his shadow is out here. Okay, so if I wanted to, what they tell me is, they want to know the rate the tip of his shadow is moving. It's moving along the x-axis. Can't talk. So that's going to be the derivative of x with respect to t. So let me take the derivative of here. Let me come in. Here's my original equation. Let me take the derivative of it. dy dt is 5/3 dx dt. Okay? There's that stray mark there that has been there since the beginning. All right, now, if I know that x is, what did he say? He's 10 feet from the base. At what rate is the tip of his shadow moving? I know that his rate, which is dx dt, I had written that over here, his rate along the x-axis that he's walking is dx dt is 5 feet per second. So I could substitute that in for this value that I just circled. That would be 5/3 times 5 feet per second would be 25/3 feet per second. So that's how fast the tip of his shadow is moving. Okay. Now part B says, at what rate is the length of his shadow changing? Now the length of his shadow changing, if you think about it, I'm going to have to flip to a new page to do the math, but let's just look at this drawing since there's so much invested in it. if the whole thing here, if y is the whole side, his length would be y minus whatever x value he's at. For instance, here he was at 10. Y minus 10 would talk about the length of his shadow if that whole length there is y. Okay, and again, y can't be bigger than 15, just because that lamppost, is 15 feet high. Okay, so now let's go ahead and go to the next page, because what I want to find, and I'm going to write it in red up here, is I want the derivative of y minus x with respect to dt. Okay, now if you think about that, I could split this up. That's the derivative. I'm going to do the math on the next page, but that's the derivative of y with respect to t minus the derivative of x with respect to t. Okay, so let me come. The derivative of y with respect to t minus the derivative of x with respect to t, because I wanted the derivative of y minus x, how long the shadow is compared to the whole length away that he's walked out from the base of the lamppost, and that's y. Okay, so if I think about that, I could substitute. I know what dy dt is. Remember, we solved for it earlier. Dy dt was, let me go back and look at my notes here. It was 5 dx dt. Okay, and that was because we had the equation y equal 5/3 x, and we took the derivative, and we got this, 5/3 dx dt. Okay, so if you look back up, you'll see, you should have that in your notes if you copy this. Now, what's dx dt? Dx dt is just 5 feet per second. Remember, that was the rate, the original rate they told us was 5 feet per second. That's how much the x is changing with respect to time. So that's why we said it was dx dt. So now, if I want to know at what rate is the length of his shadow changing, it's this, okay? So we know that dx dt is 5. So I'm going to substitute 5 for this, and that's feet per second, minus 5 feet per second, equal, okay, this is 25/3 feet per second. Now, let me get a common denominator. If I'm subtracting 5 from that, that's going to be 15/3 feet per second. And it's going to be 10/3 feet per second. That's the answer to the B part. At what rate is the length of his shadow changing? And again, if you're confused about that, we call y the whole length, and then x is where he is. His shadow would be whatever the whole y is, minus the x of where he was. That's why I took the derivative of y minus x with respect to t. But I go back to 15. I got time for a video. I was looking for another one on the video. I thought I'd look back and see what might go pretty quickly. This says the radius of a circle is increasing at a rate. So the drdt is the rate. The radius is increasing or decreasing with respect to time. And they say it is 3 centimeters per minute, so it's actually getting bigger, okay? And it says find the ratio or the rate of change of the area when A, R equals 6 centimeters and B, when R equal 24 centimeters. And so we look, and what are they talking about here? They're talking about the radius changing, and they wanted the rate of change of the area. So they want the rate the area is changing with respect to time. Well, what I need then is an equation for area. Well, area of a circle is pi r squared. So if I want the derivative of A with respect to time, pi is a constant. It would be, the derivative of r squared would be 2r, but I don't know what it is with respect to time, so I'll put dr dt. So I get 2 pi r, which, remember, that's the circumference, times dr dt. It's pretty interesting that just thinking about what you get here. Now, if r is 6, if we want to evaluate this when r is 6, we just plug in r is 6. So for A, 2 pi times the radius is 6, and then dr dt, remember they told us that up here at the beginning, the rate it's changing at is 3 centimeters per minute. So 2 times 6 is 12, times 3 is 36. That would be 36 pi centimeters per minute. And let's see, this was centimeters here, so it's actually centimeters squared per minute. Radius is centimeters, so I need to put that in so I can actually tell what's going on here. The B part, what if it's 60? Well, it's 2 pi I'm sorry, no, what if the radius is 24 centimeters? I don't know why I had 60 in my head. 2 pi r, going back to this equation, just plugging in a new r, 24 centimeters, and then the dr dt was 3 centimeters per minute. So that's going to be 3 times 24 times 6 would be 24 times 6. 144 times pi centimeters squared per minute would be the rate of change of the area with respect to time if your radius was changing by 3 centimeters per minute. So that one wasn't so hard to do. It just this is the kind of stuff you do with these things. If they mention something like area of a figure, you go get that formula because that's what you're going to use. I think one of the problems I think had to do with volume of a cone, and so you go get the formula for volume of a cone, and you do the same thing as what we're doing here.